Subscribe to Dr. Khalkar's classroom channel and press the bell icon to get latest updates. Hello everyone, I hope you are doing great. In last lecture video, I have discussed about wave-particle duality and de Broglie's hypothesis. In this lecture video, I am going to discuss about Heisenberg's uncertainty principle. So let's get started. The content of this lecture video are as follows: Heisenberg's uncertainty principle, its formula and applications, Heisenberg's gamma ray microscope, Heisenberg's uncertainty principle applied to energy and time, Heisenberg's uncertainty principle illustration by diffraction at a single slit. Followed by I will discuss about the problem solving related to the said topic. So let's see in detail one by one. Heisenberg's uncertainty principle states that it is impossible to measure or calculate exactly both the position and the momentum of an object. This principle is based on the wave-particle duality of matter. Although Heisenberg's uncertainty principle can be ignored in the macroscopic world, the uncertainties in the position and velocity of objects with relatively large masses are negligible. It holds a significant value in the quantum world. Since atoms and subatomic particles have very small masses, any increase in the accuracy of their positions will be accompanied by an increase in the uncertainty associated with their velocities. In the field of quantum mechanics, Heisenberg's uncertainty principle is a fundamental theory that explains why it is impossible to measure more than one quantum variables simultaneously. Another implication of the uncertainty principle is that it is impossible to accurately measure the energy of a system in some finite amount of time. Heisenberg's uncertainty principle also states that for particles exhibiting both particle and wave nature, it will not be possible to accurately determine both the position and velocity at the same time. The principle is named after German physicist Werner Heisenberg, who proposed the uncertainty principle in the year of 1927. This principle was formulated when Heisenberg was trying to build an intuitive model of quantum physics. He discovered that there were certain fundamental factors that limited our actions in knowing certain quantities. This principle basically highlights that simultaneous measurement of position and the velocity or momentum of microscopic matter waves will have an error such that the product of the error in measurement of position and momentum is equal or more than an integral multiple of a constant. In Heisenberg's uncertainty principle, let's say if delta x is the error in position measurement and delta p is the error in the measurement of momentum, then we can write the equation in a very simple form. Delta x multiplied by delta p is greater than and equal to h upon 4 pi. Since momentum p is equal to mv, that is mass into the velocity, then Heisenberg's uncertainty principle formula can be alternatively written as delta x multiplied by delta mv, which is greater than and equal to h upon 4 pi, where delta v is the error in the measurement of velocity and assuming mass remaining constant during the experiment. Therefore, finally we can write delta x multiplied by delta v is greater than and equal to h upon 4 pi m. So these are the equations which are important when Heisenberg's uncertainty principle is being studied. Now let's see the applications of uncertainty principle. First application is Bohr's orbit and its energy. Let's consider the electron in a hydrogen atom as shown in this figure. We don't know at any instant the position of the electron in its orbit. It might be on the left or right of the nucleus as shown in this figure. The electron position has an uncertainty plus minus r. R is the radius of the orbit. We cannot know likewise whether the electron is moving upward or downward direction. Therefore, the uncertainty in its velocity we can write plus minus v. Let's consider by taking delta x is equal to r radius nearly 0.5 into 10 raised to minus 10 of meter. So 0.5 angstrom unit. Then the uncertainty in the electron speed we can calculate delta x multiplied by delta p is nearly equal to h bar. H bar is a Planck's constant. Therefore, we can write delta x multiplied by delta p is nearly equal to h upon 2 pi. So therefore, delta p is nothing but the momentum, that is mass into velocity. So we can write this equation delta x multiplied by m delta v is nearly equal to h upon 2 pi. So by separating the term delta v, we can write delta v is equal to h upon 2 pi m delta x. So by simply putting the values in this equation, we can write delta v is equal to 6.626 into 10 raised to minus 34 joule second, which is Planck's constant, divided by 2 into the value of pi, that is 3.14, into mass of an electron, 9.11 into 10 raised to minus 31 kilogram, into 0.5 angstrom unit, that is 0.5 into 10 raised to minus 10 of meter, that is the delta x. So after solving this, we get the final value delta v is nearly equal to 2 into 10 raised to 6 meter per second. So this is the uncertainty in the electron speed. Hence, the velocity v of an electron in an atom is of the order of 1 into 10 raised to 6 meter per second and is of the same order as the uncertainty delta v. Therefore, we conclude that the uncertainty in momentum, if of the same order as the momentum, that is delta p is nearly equal to p, it means that the sharp position and momentum do not exist simultaneously for the electron in an atom. So it is not possible to describe any specific trajectory to an electron in an atom. It can be said that atomic electrons traverse the whole of the space about the nucleus, but they move most of the time at a distance corresponding to a permitted Bohr radius. Now let's calculate the energy of Bohr's first orbit. The total energy of the electron in the first orbit is given by capital E is equal to kinetic energy plus potential energy. Therefore, E is equal to kinetic energy, that is half mu square, minus potential energy is E square divided by 4 pi epsilon naught r. So we have equation E is equal to half mu square minus E square upon 4 pi epsilon naught r. So E is equal to, we can write P square upon twice m minus E square upon 4 pi epsilon naught r. So let's say this is equation number 1, where P is the momentum of the electron. Now as delta P is nearly equal to the P, then we can write above equation as P is nearly equal to h upon 2 pi delta x. So that is equal to P is equal to h upon 2 pi r. Let's say this is equation number 2. So equation number 1, we can write E is equal to h square upon 8 pi m r square minus E square upon 4 pi epsilon naught r. So this is equation number 3. But as we know that r is given by r is equal to epsilon naught h square upon pi m e square. So simply by putting the value of r in equation number 3, we can write E is equal to minus m e raised to 4 upon 8 epsilon naught square h square. So let's say this is equation number 4. Equation number 4 is the same as that is given by the Bohr theory. Now let's see the second application of uncertainty principle is particle in a box. Let us consider a particle is confined to a box of length small l. Then the uncertainty delta x in a position is delta x into delta p is nearly equal to h bar. Therefore, we can write delta p is equal to h bar upon delta x. But delta x is nothing but the length of the box. Therefore, delta p is equal to h bar upon l. So we can write the energy equation capital E is equal to p square upon twice m, which is nearly equal to delta p bracket square upon twice m. Therefore, after simplification or rearranging this equation, so we can write capital E is equal to in bracket h bar upon L bracket square divided by twice m. So that is equal to h bar square upon twice ml square. So this result agrees with the result obtained from Schrodinger's wave equation. So Schrodinger wave equations and all that theory we will see in upcoming lectures. So this is one important application of uncertainty principle. For the particle in a box, we can calculate its energy. Now see the next application of uncertainty principle, that is, let's find out why electrons cannot be present in the nucleus. The radiation emitted by radioactive nuclei consists of alpha, beta and gamma rays, out of which beta rays are identified to be electrons. Now we apply uncertainty principle to find whether electrons are coming out of nucleus. That is, the radius of the nucleus is of the order of 10 raised to minus 14 of meter. Therefore, if electron is equal to the diameter of the nucleus, thus we can write delta x is equal to 2 into 10 raised to minus 14 of meter. Therefore, the minimum uncertainty in its momentum can be written as delta p is equal to h bar upon delta x. So by simply putting the values in this formula, we can write 1.04 into 10 raised to minus 34 joule second, which is the value of h bar, divided by 2 into 10 raised to minus 14 m. So after calculating this, we get the value for momentum, that is delta p is equal to 5.2 into 10 raised to minus 21 kilogram meter per second. Therefore, the minimum uncertainty in momentum can be taken as the momentum of the electrons. Therefore, P is equal to, we can write 5.2 into 10 raised to minus 21 kilogram meter per second. Therefore, the minimum energy of the electron in the nucleus is given by capital E minimum is equal to momentum minimum into speed, that is the c. So capital E minimum is equal to 5.2 into 10 raised to minus 21 kilogram meter per second into 3 into 10 raised to 8 meter per second. So that is equal to 1.56 into 10 raised to minus 12 of joule. So minimum energy capital E is equal to 9.7 mega electron volts, which implies that if an electron exists within the nucleus, it must have minimum energy of about 10 mega electron volt. But the experimental measurements showed that the maximum kinetic energies of beta particles were of the order of 4 mega electron volt only. Hence, electrons are not present in the nucleus. So this is the very main important reason. It is subsequently established that emission of beta particles occurs due to transformations in the nucleus. The transformation of a neutron into a proton produces an electron. So this is the reason why electrons cannot be present inside the nucleus. Now let's see Heisenberg's gamma ray microscope, a striking thought experiment illustrating the uncertainty principle in Bohr's or Heisenberg's gamma ray microscope. To observe a particle, let's say an electron, we shine it with the light ray of wavelength lambda and collect the quantum scattered light in a microscope objective whose diameter subtends at an angle theta with the electron as shown in this diagram. Heisenberg's gamma ray microscope for locating an electron as shown in this figure in blue. The incoming gamma ray shown in green color is scattered by the electron off into the microscope's aperture angle theta. The scattered gamma ray is shown in red color. Classical optics shows that the electron position can be resolved only up to an uncertainty delta x that depends on theta and the wavelength lambda of the incoming light. The precision with which the electron can be located, let's say delta x, is defined by the resolving power of the microscope. So therefore, from the diagram we can write sin theta is equal to lambda upon delta x, which implies that delta x is equal to lambda upon sin of theta. It appears that by making lambda small, that is why we choose gamma ray, and by making sin theta large, that is delta x can be made as small as desired. But according to the uncertainty principle, we can do so only at the expense of our knowledge of x component of electron momentum. In order to record the quantum scattered photon by the microscope, the photon must stay in the cone of angle theta, and hence its x component of the momentum can vary with plus minus h upon lambda into sin of theta. This implies the magnitude of the recoil momentum of the electron is uncertain by delta px is equal to 2h upon lambda sin of theta. The product of the uncertainty gives delta x multiplied by delta px is equal to lambda upon sin theta multiplied by 2h upon lambda into sin theta. So after simplification we can write delta x delta px is equal to 4 pi h. This is all about Heisenberg's gamma ray microscope, in which we get the equation delta x delta px is equal to 4 pi h. Now let's see the Heisenberg's uncertainty principle equations. Heisenberg's uncertainty principle can be considered as a very precise mathematical statement that describes the nature of quantum systems. As such, we often consider two common equations related to the uncertainty principle, and they are equation number 1, delta x delta p is greater than and equal to h upon 4 pi, which is delta x delta p is nearly equal to h bar. And equation number 2 is delta E delta T is nearly equal to h bar, where h bar is the value of Planck's constant divided by 2 pi. Delta x is uncertainty in the position, delta P is the uncertainty in momentum, delta E is the uncertainty in energy, and delta T is the uncertainty in time measurement. So these are the two equations of Heisenberg's uncertainty principle in two different forms. Now let's see wavelength lambda is precise. We have equation P is equal to h upon lambda, which is precisely known, where x is unknown and uncertainty in the position of the particle is shown in this diagram. So therefore, this is the probable positions of the particles. Now let's see how position is precise. The most probable position of the particle is shown here in this diagram. There are different wavelengths waves. When they get superimposed, then we will get x is a very precise, but as resultant wave is superimposed of many waves, the uncertainty in wavelength introduces uncertainty in the momentum. So this is the uncertainty in the momentum, where the delta x is the position. So position is precise. Now let's see how Heisenberg's uncertainty principle applied to energy and time. Let's say the kinetic energy of the particle of mass m moving with velocity v is given by capital E is equal to half mv square. So differentiating this equation, we get delta E is equal to delta in square bracket half mv square bracket complete. Therefore delta E is equal to mv delta v. Therefore which is equal to V into m delta V. Therefore, momentum is nothing but the mass into the velocity. So rearranging this equation, delta E is equal to V into delta P. As we know that the velocity is nothing but the distance upon time. So V is equal to delta x upon delta t. Therefore, by putting this value in the above equation, we can write delta E is equal to delta x upon delta t into delta p. So rearranging this equation, we can get delta E into delta t is equal to delta x into delta p. Now, according to the Heisenberg Uncertainty Principle, as delta x delta p is greater than and equal to h, thus we can write delta E delta t is also greater than and equal to h. Thus, the product of uncertainties of energy and time is the order of Planck's constant. Now let's see the Heisenberg Uncertainty Principle's illustration by diffraction at a single slit. Now consider there is an electron beam which is incident on a slit along the direction x direction. So when the electron beam incident on the slit, it will get diffracted with an angle theta, and we will get the diffraction pattern of the electron beam on the screen as shown in this diagram. For light, conditions satisfied for minima is a into sine theta is equal to n lambda. This equation we have already seen in diffraction unit number 1. So very similar kind of experiment is here. Therefore, the resultant component on the screen on upper side is h upon lambda into sine of theta, whereas to the lower side is minus h upon lambda into sine of theta. So therefore, we can write for the electrons, first order minimum can be written as delta y into sine theta is equal to lambda. So the vibrations is along the y direction. So therefore, in this case, delta y is nothing but the width of the slit. As all electrons passes through slit can be anywhere within the range delta y. Therefore, uncertainty in position of electrons E, we can write delta y is equal to lambda upon sine of theta. So let's see two important cases. First is before diffraction. When the light is incident on the slit, initially the initial movement of electrons along the x direction is h upon lambda. Therefore, no component along the y direction is there. Now after diffraction, y component of momentum may be in between h upon lambda sine of theta and minus h upon lambda sine theta. Therefore, the uncertainty in momentum along the y direction we can get delta py is equal to h upon lambda into sine theta minus in bracket minus h upon lambda sine of theta bracket complete. So minus minus is plus, therefore we'll get delta py is equal to 2 into h upon lambda into sine of theta. Therefore, delta y into delta py is equal to 2h, or simply we can write delta y into delta py is greater than and equal to h. So as per this experiment, we can prove that the Heisenberg uncertainty principle with the help of diffraction at a single slit can be proved. Now let's see the problem solving related to this topic. Problem number 1. Uncertainty in time of an excited atom is about 10 raised to minus 8 seconds. What are the uncertainties in energy and in frequency of the radiation? Solution for this problem is as follows. We have equation for the energy uncertainties is delta E into delta T is nearly equal to h upon 2 pi. By putting the values in this formula, delta E is equal to 6.626 into 10 raised to minus 34 joule seconds divided by 10 raised to minus 8 electron volt. That is equal to 6.58 into 10 raised to minus 8 electron volt. In terms of joules, we have 1.054 into 10 raised to minus 26 joules. So this is the energy value we have got. Therefore, the uncertainty in frequency, we can write delta nu is equal to delta E upon H, as E is equal to H nu. So therefore, we have the value of delta E, that is 1.054 into 10 raised to minus 26 joule, divided by Planck's constant, that is 6.626 into 10 raised to minus 34 joule second. So after calculating this, we have delta nu, that is the frequency uncertainty, is equal to 15.9 megahertz. So this is the solution of problem number 1. Let's see problem number 2. An electron is confined to a potential veil of width 10 nanometer. Calculate minimum uncertainty in its velocity. So the solution for this problem is, we have formula delta x delta p is nearly equal to h upon 2 pi. So momentum is nothing but mass into velocity. So rearranging this equation, delta x into m, mass is a constant, so m delta v is nearly equal to h upon 2 pi. So rearranging this equation, we get delta v is equal to h upon 2 pi m into delta x. After putting the values in this equation, delta v is equal to 6.626 into 10 raised to minus 34 joule second. This is the Planck's constant, divided by 2 into value of phi 3.14 into mass of electron 9.11 into 10 raised to minus 31 kilogram into the width of the potential veil, that is 10 nanometers. So 10 into 10 raised to minus 9 meter. So after calculating this, we will get the value of uncertainty in velocity, that is delta v is equal to 12.1 kilometer per second. So this is the solution of problem number 2. Let's see next problem number 3. If a kinetic energy of an electron is 1 electron volt, must be measured within a 0.001 electron volt, what accuracy can its position be measured simultaneously? So the solution for this numerical is as follows. We have equation for energy E is equal to P square upon twice m. Let's differentiate this equation. Therefore, delta E is equal to 2p delta P divided by 2m. Rearranging this equation, we get delta P is equal to m delta E upon P. So we have equation for the uncertainty in position and momentum. Delta x delta P is equal to h upon 2 pi. Rearranging this equation, delta x is equal to h upon 2 pi into delta P. So we have the value of delta P, that is m delta E upon P. So simply putting that value in this equation, we get delta x is equal to h upon 2 pi into P upon m delta E. That is equal to, we can write h under root of twice me divided by 2 pi m delta E. Rearranging this equation, we can write h upon pi delta E into under root of E upon twice m. So simply putting the values in this equation, delta x is equal to 6.626 into 10 raised to minus 34 joule second divided by 3.14, that is the value of pi, into delta E, that is 0.001 into 1.602 into 10 raised to minus 19 joule into under root of 1.602 into 10 raised to minus 19 joule divided by 2 into mass of electron, that is 9.11 into 10 raised to minus 31 kilogram. So after calculating this, we get the value of delta x is equal to 1.95 micrometer. So this is the accuracy of position which is being measured simultaneously. Next, problem number 4. An electron and a 150 gram base ball are traveling at a velocity of 220 meter per second. Measure to an accuracy of 0.065%. Calculate and measure uncertainty in position of each. The solution for this problem is as follows. First of all, find out the uncertainty in velocity, that is delta v is equal to velocity into 0.065%. the velocity of both is given 220 meter per second into 0.065 divided by 100. So that is equal to 0.143 meter per second. So this is the value of uncertainty in velocity. That is the value of delta V. So first part, the uncertainty in position in electron is given by delta x E is equal to h bar upon 2m delta V. So we have value for h bar 1.05 into 10 raised to minus 34 joules second divided by 2 into mass of electron, that is 9.11 into 10 raised to minus 31 kilogram, into delta V. The value of delta V is 0.143 meter per second. So therefore into 0.143 meter per second. So after calculating this, we will get delta XE is equal to 0.4 millimeter. So this is the value for the uncertainty in position of the electron. Now let's see the second part, that is uncertainty in position of baseball. We have equation delta XB is equal to h bar divided by 2 capital M delta V. So B stands for the baseball and capital M stands for the mass of the baseball. So therefore the value of h bar is 1.05 into 10 raised to minus 34 joules second divided by 2 into mass of baseball, that is 0.15 kilogram, into delta V is 0.143 meter per second. So after calculating this, we will get delta XB is equal to 2.5 into 10 raised to minus 33 meter. So this is the uncertainty in position of baseball. This is all about Heisenberg's uncertainty principle. In my next lecture video, I'll discuss about wave function and its physical significance. So please don't miss my upcoming lecture. Thank you. Below this video, in the description, the link of important information related to this video is given. Please go through it. Please like and share this video and subscribe to Dr. Khalkar's classroom channel to get the notifications about my upcoming videos. Thank you.